Hey guys, welcome to the second half of this unit. So we're going to talk about some diffraction, wave interference, and reflection. We don't really have any calculations for this. It's all kind of knowledge stuff. So, reflection. Both particles and waves reflect off of a surface, and the law of reflection states that the angle of incidence is equal to the angle of reflection. And that sounds a lot more confusing than it is. I'll show you on a picture on the next slide, and it's not hard at all. So when we measure the angle of incidence and the angle of reflection, we measure it from, not from the surface, but from a normal line, which is just an imaginary line that is perpendicular to the surface. So I'll point that all out here. So you can see that the normal line is drawn on right here, right? And it's 90 degrees from the surface. So this is my incoming ray. So say this was 20 degrees here. Well, it's going to bounce off at 20 degrees as measured from the normal. So the angle of incidence equals our angle of reflection. So the light ray bounces off like that. So nothing difficult at all about that. These are the types of questions that you can see, and it's more of like math triangle stuff. Well, if this light ray comes in here and then bounces off there, if this is 36 degrees, then this is going to be 36 degrees as well. And we know that our normal line from the surface is 90 degrees. So if this is 36, well, if we go 90 minus 36 degrees, then we get, what is that? I'm trying to do it in my head. 54? Yeah, this is 54 degrees. And then this makes a triangle here. We know triangles all make 180 degrees. So if we go 180 minus 54 minus 110, we can find out this angle here, right? I don't want to do that in my head. So 180 minus 54 minus 10 gives us, oops, not 10, 110. Gives us 16 degrees. So this is 16 degrees here. And then let me just extend the surface here. So this is our angle of incidence. This is our angle of reflection. So this is going to be 16 degrees. And here's our normal line. So if we go 90 minus 16, then we can find this angle here. And 90 minus 16 will give us 74. So this would be 74 degrees. So just like that. That is all. Okay, another type of question that you can have, this is more of a trig question, but you need to know reflection. So a sonar signal is a sound wave sent underwater by ships to locate objects underwater. A boat on the surface of a 100-meter deep lake sends a sonar signal at an angle of 30 degrees from the bottom of the lake. At what distance from the boat on the surface of the lake should the buoy with the sonar signal receiver be placed? So I'll draw a picture of what's going on here. So we have our water here, and then it says that our lake is 100 meters deep, and here's our boat. There we go. And then here's our buoy over here. So it sends a sonar signal, and then it hits the bottom of the lake, and then it bounces up and goes to that buoy there. And it says that sends a sonar signal at an angle of 30 degrees from the bottom of the lake. So this is 30 degrees. So we know that this is 30 degrees, right? And we want to know, well, how far, what's this distance here? How far does that buoy need to be placed from the boat? So it's just a trig question, right? So this makes a triangle. We can use SOHCAHTOA to do it. We have our angle, and we have opposite, and we want to find adjacent. So opposite and adjacent is tan. So I can just set it up as tan of 30 degrees is equal to opposite over adjacent. Right? Move the adjacent up here, move the tan 30 down below, and I can find out what this distance is here. So 100 divided by tan 30 gives us 173.2 meters, right? And this triangle and this triangle are the exact same triangle. So this is 173.2. So I multiply it by 2, and I get my distances 346. And we have 3 sig digs, so that's enough. So 346 meters would be my answer. So it's more of a trig question than a reflection question. Okay, so that's reflection, that's it. Interference of waves. So when two particles meet, there's a collision that affects the path and speed of the two particles afterwards. So you can see my one ball hits my other ball. The blue ball is stationary. The green ball, it looks like it's going east, right? After the collision, the green ball is going north of east, and the blue ball is going south of east, so their paths and speeds are permanently affected. But with waves, it's different. So when two waves meet, they interfere with each other temporarily, but once they pass through each other, they continue through as if they'd never met. So let me show you what that looks like. Okay, so we have our two waves here. They're going to come together here. They're going to interfere. The wave changes, and then it passes through like they've never met. Right? These waves are going to come to, these waves come together here. They get bigger, and they pass through like they never met. So what's changing is the amplitude of the wave. So now these waves are meeting out of phase because one's on the top and one's on the bottom, and they canceled out there for a second, and then they pass through like they never met, right? And these waves meet in phase because they're both on the bottom, right? The amplitude gets bigger for an instant, and then they pass through like they'd never met. So when two or more waves meet, their interference will produce a resultant wave that is the sum of the individual waves. And when we talk about the sum of the waves, we're talking about their amplitude, how high or low a wave goes. So depending on if the waves are in phase or out of phase, then there are two types of interference that we can see. We can see constructive interference, and we can see destructive interference. So we'll talk about constructive first. So when two waves meet and they're in phase, they will temporarily produce a maximum wave that is larger than the individual wave. When a crest meets a crest, they will join to form a supercrest, and after they meet, they will continue on the original path as if they had never met. So to show you in a picture here, I have crest meeting with crest, right? So these waves will add together, and we get a much bigger amplitude, right? Trough meets with trough. So those troughs are in phase, so we get a much bigger amplitude, right? If we sort of draw our equilibrium line in here, we can see that the amplitude gets bigger. So the amplitude is about 2 boxes high here for the crest, and now it becomes about 4 boxes high. But the wavelength and the frequency should not change from interference. Destructive interference is when they meet out of phase and the two waves can cancel out, or if they're not exactly the same, they can produce a smaller or minimum wave temporarily. So when crest meets a trough, they will cancel out temporarily and then pass through as if they'd never met, right? So here, let me draw my equilibrium line. Ooh, that was bad. We have crest meeting up with trough and trough meeting up with crest. So this is kind of like +2 and -2. If we add them together, it gives us nothing, right? This is -2 and this is +2. It equals out and gets nothing. So this is the interference patterns. So waves can be either moving towards each other or away from each other. So each of these situations will affect what that resultant wave will look like. If the waves are moving in the same direction, completely in phase, then they'll be one wave with large crests and large troughs. So this is our wave 1, this is our wave 2, and we get these bigger amplitude. And you can see the wavelength frequency aren't changed. So an example of this would be 2 trumpets in an orchestra. So if you have 1 trumpet, it's not very loud, but if you have 2 trumpets, it's going to be louder. And that's what louder is. Louder is a bigger amplitude. So they're playing the exact same thing. They're in phase, they're standing beside each other, and we just get a louder version of the same sound, a bigger amplitude. So if your waves are moving towards each other and are the same frequency, you will create a standing wave. So a standing wave has areas of movement called nodes and areas of no movement called antinodes. So this is much better if I do this in person, but this is all we have right now. So you can see that we have two waves here. We have a blue wave that's traveling this way, and we have a red wave that's traveling this way. So these waves are traveling towards each other, and this black line shows what the interference pattern is from the wave. And because they're always changing, this interference pattern also changes. So we get this area where it moves quite a bit, and an area where it moves quite a bit. So these areas right here and here are called antinodes. And then we have this area where it doesn't move at all. Those are called nodes. So we have areas of antinodes and nodes, and it looks like a standing wave because the wave just stays in one position and just goes up and down, right? But it's just a result of those two waves that are interfering with each other in the background. So we can get an interference pattern from any type of wave, including a water wave. So this video shows a water wave, and what you have on this end is you have a wave generator. So wave generator is just like a platform that moves up and down. So that's what the West End Water Park has. It just creates waves when the platform moves up and down. But this is a special type of wave that has a wave generator on both sides. So you have a wave generator moving up and down on this side, and at the exact same frequency, you have a wave generator moving on this side. And what you create in this pool is a standing wave. So check out this video. So calculate the resulting interference pattern when a wave of 2.5 centimeters and a second wave of 2 centimeters combine in phase and then out of phase. Okay, so I think this will be easier if I draw this on my whiteboard. So that's what I will do. Okay, so if we draw a 2.5 centimeter wave, so the 2.5 centimeters refers to the amplitude. So this is my 2.5 centimeter wave, where this is 2.5 centimeters, and this is 2.5 centimeters. Okay, I'm going to get them to meet up in phase first. So I'm going to draw another wave, and I'm going to try to draw it smaller, like that, where this is 2 centimeters, and this is 2 centimeters. So we want to know, what is that resultant wave going to look like? Well, this is constructive, this is in phase. So I'm just going to add up these two numbers. And what I'm going to get, oops, bumped my calculator there. What I'm going to get is I'm going to get a much larger wave. And this is going to be 4.5 centimeters, and this is going to be 4.5 centimeters as well. So that's if they meet up in phase. If they meet up out of phase, the way that I would draw that is I would draw it just the other way, like that. And it's still 2 centimeters, and it's still 2 centimeters. And I still add up these two numbers, but this is positive 2 centimeters. This is negative 2 centimeters, negative and positive. So when these two waves add up, I have positive 2.5, negative 2. So I'm going to get a wave that's 0.5, and I have negative 2.5 and positive 2.5. So this is going to be 0.5. So this is what they look like when they meet up out of phase destructively, and then the other one was in phase and constructively. There we go. So the last thing that we need to know is diffraction. This is kind of the weirdest one that people have a little bit of trouble with. So what diffraction is it's the bending or spreading out of waves as they pass through an opening or around a corner. So waves diffract, particles do not diffract. Okay? And we'll talk about what diffraction looks like. I'll draw a picture on the next slide. So things you need to know about diffraction are as wavelength increases, you need to know that the amount of diffraction increases. So if you want more diffraction, bigger wavelengths are better. Lower frequency diffract more than higher frequency, because remember that using the universal wave equation, we did that already. Yeah, we did the universal wave equation. As I increase my wavelength, I decrease my frequency. So we want lower frequency notes. Okay, and the opening the wave diffract through must be the same size or less than the wavelength to make it work. Okay, so we're going to compare particles and waves, and we're going to talk about what diffraction looks like with both. Okay, so if I send, let's say this is me. If I've been having a bad day and I bring my paintball gun to school and I shoot paintballs, and this is the opening of my doorway. This is a hallway out here. I shoot paintballs out my opening here, right? Only the paintballs that go through the opening are going to make it through. So if these are the lockers outside of my room here, I would get, let's change my color. I would get paintball splatter just the size of my opening, right? I'd get a whole bunch of splatter here. So if there was a person over here, well, they wouldn't get hit with the paintballs. Or if there's a person here, they wouldn't get hit with the paintballs. But if there's a person here, they would get hit with those paintballs. And that's how particles work. So waves work a little bit differently. So if I send a wave through, so this is me. Oops, I guess I don't need to be that far back. But anyways, this is me right here. And instead of bringing a paintball gun to school, I decide to yell at students in the hallway. So I send a sound wave through. So this is my sound wave coming off of me. Oops, there's my arms. And what's going to happen is that as those waves go through this opening here, they're going to diffract. And what that means is those waves bend as they go through that opening. So they bend around the corner like that. And what that means is if there was a person here, they would get hit with those sound waves. If there's a person here, they'd get hit with those sound waves. If there's a person here, they'd get hit with the sound waves, right? Because the sound waves would continue as they go along. And the pattern that we'd get on the wall with the sound waves, if we could see them, is we'd still get the biggest amount of sound waves right through that opening, but we'd also get quite a bit of sound waves hitting off to the side because it bends around that opening. So that's what diffraction is. It's light bending, or sorry, light. I've been doing too much light stuff. Sound bending as it goes through the opening. And as we increase the size of our opening, what we'll find, well, if I'm shooting particles through there, so now I have a bigger doorway and I shoot my paintball gun through there. Paintball gun, it's not messed up. So the paintballs will go through, and what we'll see is right, this pattern on the wall. Lots of paintballs here, but still none around the corner. Because, yeah, that's what we'll see with particles. So because we have a bigger opening with a wave, remember that the opening the wave diffract through must be the same size or less. Small openings make diffraction work better. So if I send my sound waves through this bigger opening, what's going to happen is those waves aren't going to diffract as much. They're still going to bend a little bit, but they're not going to bend all the way around the corner like the first situation. So a person standing here probably wouldn't get hit with my sound waves as well. They wouldn't be able to hear it as well, right? The person would still be able to hear it here. And the pattern that we get on the wall there would be, we'd get a lot of sound waves right through the opening, but we'd get less diffraction, right? We'd get less along the sides, right? This one went the whole length of the wall. This one just went a little bit. And as that opening gets bigger, well, light and particles, or not light, waves and particles kind of look very similar, right? But when that opening's small, they do very different things. So here's another example. So say you have a building here, and then you have a wall here. So this car travels by and it's got a high frequency horn. So a high frequency horn would be like beep, 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 beep. And he's beeping his horn, beep, beep. Well, if you were standing in here, or this was one of your apartment buildings here, you wouldn't be able to hear that high frequency noise because those sound waves wouldn't diffract over that wall. But if this is like a really low sound, a low frequency, like right, those sound waves would be able to diffract around that wall. So if you're on the bottom floor here, you'd still be able to hear that really low sounding horn compared to the high sounding horn. So that's diffraction. And then here's an image of diffraction that's really cool. These are water waves. And in these water waves, so the current is sort of traveling this way. And you can see this beautiful diffraction pattern as it goes through the opening. So what you would see, if you were standing on the rock here, you would actually get hit with waves if you were standing here, and those waves would be coming from behind because those waves are bending and diffracting, and you'd get waves crashing on the backward shore here. That's what diffraction is. Okay, so I have a board question for you. Pretty straightforward. Just give this a go. I want you to draw, come on, there we go. Just the first one. I want you to draw what the diffracted waves would look like in this situation and this situation. So when we draw our waves like this, what we're doing is we're sort of doing an overhead view, and all those lines represent those crests of it. Actually, I guess it would be like compression and rarefaction, but it's the same idea. So those crests would be compression, and if they were sound waves, and that's what we would see. So these are all crests. Or compressions of diffracted waves. Okay, so I want you to draw what it would look like in both situations. So pause the video and then try it yourself. Okay, so these are longer wavelengths. So longer wavelength is going to diffract better. So it would look like that. It would bend around the corners. And these are shorter wavelengths. They're not going to diffract as well. So you would just sort of draw it like a Wi-Fi symbol like that. It wouldn't bend around the corners. Okay, give this one a go. So you don't need an opening. You can bend around a corner as well, like that sound shade that I showed you. So draw on what the diffracted waves would look like. Okay, pause the video. Okay, these are longer wavelengths, so these are going to diffract better. So they're going to bend around that opening, and this one isn't going to diffract as well. They're just going to kind of go straight forward, and they're not going to bend around that corner. Okay, one last thing we can talk about is double slit diffraction. This is more what we do in Physics 30, but we talk about diffraction and interference. And this is something that light does, and sound waves would do this as well. So if I send a signal through an opening, I would get a diffraction pattern. And if I send a signal through another opening, I would get another diffraction pattern. So if I put these openings close enough, what I can get to happen is I can get these diffraction patterns to interfere with each other, right? So this is a crest, this is a crest, this is a crest, and what I'd get is I'd get crest matching up with crest, I'd get constructive interference down the middle there, right? So if I had a screen over here, I'd get a super bright light or a super loud sound here. And then here I have crest matching up with crest, so I'd get a loud sound or a bright light here, loud sound or a bright light here, right? Same thing here, same thing here. And then in between those constructive interference, I get this zigzag, which is crest meeting up with trough. So I'd get bright, dim, bright, dim, bright, dim, bright, dim, or I get loud, quiet, loud, quiet. And if you think of speakers, so if these are speakers over here, If you put two speakers by each other and they go through an opening, well, they're going to diffract and they're going to interfere with each other, so you can get loud sounds and quiet sounds. And if you're in a theater with a whole bunch of speakers, you can get areas where it's louder and quieter. So here's a stupid little clip from Big Bang where Leonard tries to avoid Sheldon by going to the theater with his girlfriend at the time, and Sheldon tracks him down and does a little thing before movies start, which isn't totally crazy because he's just talking about diffraction and interference. So check out this video. Okay, this is our homework. So not much homework, not any calculations with this. So this should be pretty quick and easy for you to do. And if you have any questions, just let me know.